Now coming to the next part of the P block elements, we are going to continue with nitrogen. So before going to the preparation of nitrogen, as you can see on the screen where I am showing you the preparation of nitrogen, but before going to the preparation, let me tell you about the anomalous behavior of nitrogen, that is which I left you in the last AV. Nitrogen, the first member of the group 15, differs from other elements of the group in several respects. In several respects, it differs from the other elements of the group. The anomalous behavior of nitrogen is due to its small size, due to high ionization energy, due to high electronegativity, and the absence of d orbitals in its valence shell. Again, I repeat, the anomalous behavior of nitrogen is due to its small size, due to its high ionization energy, due to its high electronegativity, and due to the absence of d orbitals in its valence shell. The main points of difference between nitrogen and other members of the family are, other members of the group are, at ordinary temperature nitrogen is a gas while other members are solids. Note it, very important this one. At ordinary temperature nitrogen is a gas while other members are solids. Nitrogen exists as a diatomic molecule while phosphorus and other elements of the group exist as tetraatomic molecule like P4, AS4, SbF4, etc. Due to its small size and high electronegativity, nitrogen is the only element of the group which can form hydrogen bonds in its compound. It can form hydrogen bond, but other elements do not. Nitrogen has a tendency to form p-pi multiple bonds, while other elements forms d-pi overlapping, we can say that. Nitrogen shows a wide range of oxidation state from -3 to +5. The other elements of the group shows a limited number of oxidation state which I have discussed with you in terms of oxides and fluorides. Ammonia is a stable, that is hydrides of nitrogen is a stable and it is basic in nature, while the hydrides of the other elements are less stable and less basic in nature. Nitrogen does not form pentahalides like we have seen in case of phosphorus, PCl5, but in case of nitrogen we don't see any NCl5. I told you the reason also, because due to the absence of d orbitals in its valence shell, while all other elements of the group forms pentahalides. Got it? Due to the absence of d orbitals, nitrogen does not form complexes. Other elements does undergo complex formation. Now we will see the preparation of nitrogen. Actually, nitrogen was discovered by Rutherford, Daniel Rutherford, scientist, we can say that. Lavoisier established its elemental nature and named it as azote. We can say that. Azote means without life, it does not have any life, that is called azote. There is lifeless air, rather I should say that. Nitrogen is derived from the word niter, which is a well-known nitrogenous compound, that is KNO3, we can say that. Clear? It occurs in the free state as well as in the combined state. In nature we get the nitrogen, we can say that. In combined state we are getting it in the form of KNO3, NaNO3 and ammonium salt, so on, we can say that. In the preparation of nitrogen, you can see ammonium chloride, when it reacts with NaNO2, it gives you NaCl, H2 and N2 gases being, we are getting it. Alright, we are getting, along with N2, we are getting small amounts of nitric oxide and nitric acid are also formed in this reaction, but the nitrogen thus obtained is purified by passing the evolved gas through aqueous sulfuric acid solution containing potassium dichromate. Alright, potassium dichromate, what it will do? It will convert nitric oxide to nitrogen dioxide, which is a reddish brown colored gas, and nitrogen will be collecting it by the downward displacement of water. Got it? The first reaction which you can view, got it? That is NH4Cl reacts with NaNO2 form NH4NO2 and NaCl. NH4NO2 on heating will give you, that is nothing but N2 plus water. It can also be prepared by heating ammonium dichromate, which gives you nitrogen. Ammonium dichromate are red crystals of ammonium dichromate which is heated. Red or orange colored crystals also can be said. When it's heated, a violent reaction takes place accompanied by flashes of light and evolution of nitrogen gas. By oxidation of ammonia, that is also it can be done. That is when ammonia is oxidized in presence of copper oxide and chlorine, that is excess ammonia reacts with chlorine, it gives you nitrogen gas. Alright, when ammonia reacts with copper oxide, NH3 plus CuO gives N2 plus water plus Cu. Similarly, 8NH3 plus 3Cl2, you read it in lower classes, it gives you N2 plus 4H, NH4Cl, we can say that. It can also be done by heating sodium azide, like NaN3 on heating, sodium azide, NaN3, it gives you nitrogen. Barium azide also on heating will give you nitrogen. Got it? Now this is the preparation of that is your ammonia. But before going to the preparation of ammonia, let me say you that nitrogen commercially in the large scale, in industrial scale, nitrogen is prepared by fractional distillation of the liquid air. We can say that liquid air, on going for fractional distillation, we get the nitrogen gas. That is, not only we get the nitrogen gas, we basically get the nitrogen liquid, then we convert it into gaseous state. Got it? In fractional distillation, both the substance we get oxygen and nitrogen, but nitrogen is being collected because we can collect it by fractional distillation by difference in their boiling point. We can say that. Clear? Liquid nitrogen being more volatile than liquid oxygen, distilled out first, leaving behind liquid oxygen. We can say that. It's a colorless, odorless, and tasteless gas. If you see its properties, it's non-poisonous, but animals die due to the lack of oxygen. We can say that. It has got very low solubility in water. Nitrogen, we can say that. It is almost unreactive at ordinary temperature, nitrogen, because due to the presence of 3 bonds, triple bond, we can say that, which is highly stable. The chemical inertness of nitrogen at ordinary temperature is due to the stability of N triple bond N molecule. N triple bond N molecule. Got it? The N triple bond N has a very high bond enthalpy. Due to very high bond dissociation enthalpy, nitrogen is almost unreactive with ordinary temperature and with other reagents also. I am saying you again, ordinary temperature, mind it. Nitrogen reacts with the metals to form nitrides, like magnesium reacts from magnesium nitride, aluminium nitride, calcium it forms calcium nitride. It reacts with hydrogen in Haber's process, which you are going to study it now. Got it? We'll give you ammonia, we can say that in this way. Then if you see nitrogen fixation, it is there. The process of conversion of atmospheric nitrogen into useful nitrogenous compound is called the fixation of nitrogen. It can be done by lightning discharge by symbiotic bacteria. An artificial fixation is also being done. Conversion of atmospheric nitrogen into ammonia and other compounds, useful compounds, we can say that, which is known as artificial fixation of nitrogen. Conversion of nitrogen into ammonia and other useful compounds, which is used for synthetic purposes, is also called as artificial fixation of nitrogen. We can say that. Now coming to ammonia, as you can see it on the screen now, that ammonia can be prepared by heating urea, which gives ammonium carbonate. Ammonium carbonate further gives you ammonia. On the screen you can see ammonium sulfate. By heating ammonium sulfate also you can get that is ammonia with sodium hydroxide. Alright, ammonium sulfate, when it is heated with NaOH, it gives you ammonia plus water plus sodium sulfate. Ammonium chloride, when it is heated with KOH, it gives you ammonia plus water plus KCl. Similarly, when ammonium chloride is heated with slaked lime, which is the lab preparation of ammonia, we can say that, and is heated with slaked lime, it gives you ammonia plus water plus calcium chloride, so to say. Clear? So in this way we can prepare ammonia in this manner. This is the Haber's process for the preparation of ammonia. In the Haber's process, the temperature is what you can say kept at around 450 to 500 degrees centigrade temperature. The pressure is very high, 200 to 900 atm pressure, and the catalyst is being taken. You can say that first we pass the nitrogen and hydrogen gas through the reactor, that is compressed hydrogen nitrogen gas, rather I should say, it is being passed through the particular reactor in the ratio of 1:3, nitrogen and hydrogen. Got it? In the ratio of 1:3, nitrogen is to hydrogen, and if it is hydrogen is to a nitrogen, then 3:1. Got it? And it's compressed means the pressure is 200 to 900 atm pressure. The gas is being compressed and it is being passed into the reactor, which contains a catalyst, suitable catalyst is your iron and is a catalyst, and molybdenum is a promoter, we can say that. We can also use that is small amount of K2O and Al2O3 as a catalyst. Potassium oxide and aluminum oxide is a catalyst, we can use it. Then from the catalytic chamber, it goes to the what you can say the coolant. The refrigeration coils are there, where the gaseous ammonia is being converted into the liquid ammonia, which is being further collected. The uncombined nitrogen and hydrogen comes from the coolant, and again it goes through the compressor to the catalytic chamber, and finally it is being converted into liquid ammonia. Got it? In this way the process goes on, we can say that. So in this way we can prepare, that is what you can say, ammonia by the Haber's process. So Haber's process is nothing but N2 plus 3H2 will give you ammonia, and the reaction is exothermic in nature. So what you find is that initially it is being heated. As the reaction is exothermic, initially it is being heated. After that, heating is not required, because the heat which is liberated during the course of the reaction, that only carries the reaction forward, we can say that. Alright, that only carries the reaction forward. The catalyst, already I said you, iron catalyst, molybdenum is a promoter, we can say that. Clear? So in this way we can prepare, that is ammonia, by the Haber's process. The plant, you can see it here. Got it? So now how to dry the ammonia gas? The moisture present in ammonia may be removed by passing it through the glass tower packed with quicklime, calcium oxide. It cannot be dried by using concentrated sulfuric acid or anhydrous calcium chloride or phosphorus pentoxide, because in all the cases it reacts. Got it? With anhydrous calcium chloride it forms an addition product. With phosphorus pentoxide it forms ammonium phosphate. With Kong sulfuric acid it forms ammonium sulfate. The only thing left is your calcium oxide, that is your quicklime, which is used as a drying agent for drying ammonia gas. After preparing ammonia gas, ammonia is a colorless gas with a characteristic pungent odor. It causes tears in eyes, we can say that. It is lighter than air, therefore it is collected by the downward displacement of air. It is highly soluble in water, highly. Got it? That is, we can say that 1 volume of water dissolves around 1300 volumes of ammonia at 273 Kelvin and 1 atm pressure. It is highly soluble, and the solubility is due to the presence of intermolecular hydrogen bonding with water. The high solubility of ammonia. Got it? It is due to the intermolecular hydrogen bonding with water. Got it? It liquefies to a colorless liquid on cooling under pressure. We can say that its latent evaporation is also very high, and due to that reason it can be used in refrigeration. Got it? It has got a very high latent evaporation, around 1380 joules per gram. The latent evaporation is. For that reason it is extensively used in refrigeration purposes. That is ammonia, we can say that. Now these are the different reaction of ammonia and also the group 15 compounds, we can say that. P2O5 reacts to form phosphoric acid. Ammonia forms ammonium phosphate with H3PO4. Ammonia reacts with bleaching powder to form nitrogen gas. Ammonia reacts with bromine to form nitrogen gas again. There is the reduction properties of ammonia, the oxidation of ammonia. We can say that catalytic oxidation of ammonia, NH3 plus 5O2. We can see first, second, third, fourth, fifth reaction. Clear? We are getting NO plus water. Similarly, a mild and harmless explosive is being produced when ammonia reacts with Ni3. It forms an addition product. That is, we can see that it forms hydrazine. Ammonia when reacts with NaClO, that is sodium hypochlorite. Got it? It forms hydrazine, NH2.NH2. Now next we will come to the nitric acid. Alright, we'll come to the nitric acid, so to say. There are different compounds related to the nitric acid. We will see it. And nitric acid is basically it is being prepared by Ostwald process. Nitric acid, we can say that it is being prepared by the Ostwald process. So first we'll see the preparation of the nitric acid, the lab preparation of nitric acid. In the lab preparation of nitric acid, what you can see is that we are taking potassium nitrate and concentrated sulfuric acid. We are taking potassium nitrate, KNO3, and Kong sulfuric acid. In a glass retort you are heating it. So when you are heating in a glass retort, nitric acid is being produced, and this nitric acid is allowed to cool down. What you can say, the vapors is allowed to cool down, and we are collecting the liquid nitric acid in a round bottom flask. We can say that we are collecting the liquid nitric acid in a round bottom flask. So potassium nitrate or sodium nitrate, when it is heated with concentrated sulfuric acid, we are getting the nitric acid, the liquid nitric acid, we are getting it. Nitric acid is a colorless liquid. The impure acid is generally yellow due to the presence of nitrogen dioxide as an impurities. You can see that brown fumes is nothing but that is of nitrogen dioxide only, the reddish brown fumes, which you can see it there in the screen while preparing nitric acid. Pure acid boils at a particular temperature like around 350 Kelvin, we can say that, and freezes to a white solid. The nitric acid, it is miscible with water and forms a constant boiling mixture. It forms an azeotropic mixture which contains 68% nitric acid and boils at 394 Kelvin. Got it? It has an extremely corrosive action on the skin and causes painful blisters. Nitric acid, we can say that. painful blisters it causes, nitric acid. Got it? And the pure what you can say, the nitric acid, we can say it's 100% nitric acid, can be obtained by cooling fuming nitric acid. Now what is fuming nitric acid? Fuming nitric acid is nothing but 98% concentrated nitric acid is called as fuming nitric acid. Got it? Dilute nitric acid, as I just now I said you, it forms a constant boiling mixture at 60 what you can say 68% nitric acid, which forms a constant boiling mixture. This is generally used as concentrated nitric acid in the laboratory. Further concentration may be done by concentrating under high pressure in presence of sulfuric acid, when we get 98% nitric acid, which is called fuming nitric acid. Now nitric acid about 100% can all be obtained by cooling fuming nitric acid in a freezing mixture when crystals of pure nitric acid get separated. So you see three types of nitric acid residue. One is your constant boiling mixture 68%, which is used in the lab as concentrated nitric acid. Then on further boiling it under high pressure in presence of concentrated sulfuric acid, we get 98% nitric acid, which is called fuming nitric acid. Fuming nitric acid is for the cooled, got it, to obtained freezing mixture, which is called as the crystals of nitric acid, we can say that. Clear? So in this way, this is about your nitric acid, so to say, the preparation of nitric acid. Now here you can see the Ostwald process. I have shown you here in the Ostwald process. There we are taking ammonia gas and oxygen gas in the ratio 1:8 or 1:10 also, I should say, can be taken. When large quantities of oxygen is taken, large quantities of air is taken compared to that of ammonia. So why? Because oxygen or air is being used, you will see in the all the process for the preparation of nitric acid in Ostwald process. Got it? Oxygen or air is being used in all the steps for the preparation of nitric acid in the Ostwald process. So right from the beginning itself, we are taking a large amount of air, we are taking a huge volume of air, we are taking it. So hence the ratio of ammonia to oxygen or a ratio of ammonia to air is 1:8 or 1:10 by volume, we can say that. Clear? So ammonia and oxygen is being heated in presence of platinum, that is your catalytic oxidation to form nitric oxide and water. Alright, ammonia and oxygen is being heated first of all in presence of platinum, that is your catalytic oxidation of ammonia is being done to form nitric oxide and water, and the reaction is highly exothermic in nature. So initially heating is required, after that heating is not required, we can say that. Whatever the heat is being liberated, that only it carries the reaction forward. Alright, it is being carrying the reaction forward. The temperature is maintained by itself, because the process is exothermic and therefore no more heating is required, no more further heating is required. The gases coming out from the catalytic chamber, you can see it on the screen, that is a platinum gauze, that is the gases coming out. Which gas? Nitric oxide gas. Coming out from the catalytic chamber is led to aluminium or chrome steel vessels, we can say that, where they are being cooled. Rather I should say it is being passed through the cooling towers where it is being cooled. Why? Because if you don't cool the gas, then a reversible reaction may occur. For that reason we need to cool it. So next it is being passed to the oxidation chamber. You can see it on the screen. In the oxidation chamber, nitric oxide reacts with oxygen to form nitrogen dioxide, and the temperature is maintained around 50 degrees centigrade, because just now I said you, if the temperature is very high, then nitrogen dioxide formed will be reversible. Again it will form nitric oxide back. So hence before that only we need to see that the temperature is less, it is being lowered down to around 50 degree Celsius. Then after that it goes to the absorption tower. The tower consists of acid proof flint, you can see it on the screen. It is being packed with quartz, we can say that, from the top, and from the top water is being spread, isn't it? You can see in the screen that from the top the water is being spread, you can say. Clear? The spraying of water is being done from the top. Nitrogen dioxide mixed with excess of air, because already in the beginning I have taken more amount of air, 1:8 or 1:10 by volume, we have taken ammonia is to oxygen. So nitrogen dioxide mixed with excess of air which is introduced in the tower. The reaction takes place, that is nitric oxide plus water, it forms nitrogen dioxide plus water, it forms nitric acid, and NO NO further reacts with oxygen to form NO2. Again NO2 reacts with water to form nitric acid. In this way the process goes on, the cycle goes on till all the nitrogen dioxide is being converted into nitric acid. Alright, that cycle goes on, that is nitrogen dioxide reacts with water to form nitric acid and NO reacts with oxygen to form again NO2, again NO2 again reacts with water to form nitric acid. In this way the cycle goes on till all the nitrogen dioxide and nitric oxide is converted into, that is nitric acid. And nitric acid is collected from below, you can see in the screen. Alright, and the waste gases is being given out from the top, we can say. In this way nitric acid is being prepared in industries by the Ostwald process, we can say that. Nitric acid, we can say nitric acid, as it is an acid, it is acting also as an oxidizing agent. Not only it's an acid, it also acts as a very strong oxidizing agent. So it gives you several oxidized products, like sulfur is oxidized to sulfuric acid. Alright, and you can see it here, that is with concentrated nitric acid, when it reacts H2S, it forms H2O plus NO2 and S. With dilute nitric acid it forms H2S, it forms water, NO and S. Ferrous sulfate is being converted into ferric sulfate, we can say that. Clear? So when nitric acid reacts with iodine, it forms HiO3. When nitric acid reacts with phosphorus, it forms H3PO4. When nitric acid reacts with carbon, it forms carbon dioxide. So several compounds gets oxidized in presence of nitric acid. Several compounds like Ki, potassium iodide, reacts with HNO3. It is not there in your screen, you can write it down. Ki plus HNO3 will give you KNO3 plus NO plus I2 plus water. Ki plus HNO3, you can balance it, KNO3 plus NO plus I2 plus water. Alright, then we can say Sc, selenium, is oxidized to selenous acid. Selenous acid, Sc plus HNO3 will give you H2SCO3 plus NO2 plus water. H2SCO3 plus NO2 plus water, we can say that. Clear? So in this way, these are the steps I have given you, the schematic diagram. The steps to how do we prepare nitric acid, that is ammonia reacts with oxygen, catalytic oxidation to form nitric oxide. Nitric oxide reacts with oxygen to form nitrogen dioxide in the oxidation chamber, and in the absorption tower it gets converted into nitric acid. And NO, I to study you, NO first reacts with oxygen to form NO2, NO2 again reacts with water to form again nitric acid. Alright, the schematic diagram, the stepwise diagram I have given you. So in this way, this is about your nitric acid, which I talked with you, the nitric acid, what are the uses and all those things you came to know. Now phosphorus, little bit, once more I am saying a little bit of phosphorus. Now phosphorus actually that is an exposure to light. White phosphorus turns yellow, therefore it's called as yellow phosphorus. That is a P4S3 is the most stable sulfide of phosphorus. It is used in strike anywhere matches, means in the matchbox you can see on the box, the where you are striking the what you can say, the match you can say. So that is, it is coated with phosphorus trisulfide. It is being coated with phosphorus trisulfide, where we are taking the matchstick and you are striking there. That is said to be as matches containing P4S3, KClO3, filter and glue. The friction between the match and the sandpaper on the side of the matchbox initiated a valent spark between P4S3 and KClO3. These generate sufficient heat, causes matchstick to burst into flame. For that reason, matchstick burns when you strike it. It is obtained by heating white phosphorus at 573 Kelvin. How do we get this phosphorus? It is being said out without contact in air. It is a hard, crystalline, colorless, odorless solid, not colorless, that is odorless solid with iron gray luster. It is non-poisonous in nature. It does not react with caustic alkalis. This property is used in separating red phosphorus from white phosphorus. It's very important. It does not react with caustic alkalis, but red phosphorus does. We can say that. Clear? So next is black phosphorus. That is, we can say that black phosphorus. We have already read red phosphorus. Black phosphorus, it is prepared by heating white phosphorus to around 473 Kelvin under high pressure in an inert atmosphere. Alright, black phosphorus is being prepared by heating, that is white phosphorus at 473 Kelvin under high pressure in an inert atmosphere. Black phosphorus is being prepared. Black phosphorus, it has two types, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803 Kelvin. Alright, and black phosphorus is being formed when white phosphorus is heated, just now I said you, at 473 Kelvin under high pressure, that is 4000 to 12,000 atm pressure. Now if you see, the three allotropic form of phosphorus differ widely in their chemical reactivity. White phosphorus is the most reactive, I have told you earlier, while black phosphorus is the least reactive in nature. Therefore white phosphorus is stored under water to protect it from air, while red and black phosphorus is stable in air. Alright, white phosphorus is stored under water, mind it, white phosphorus we are storing it under water to protect it from air, while red and black phosphorus is stable in air. It's stable, it's quite stable in air. This is the structure of white and red phosphorus. Once again I am showing you, I have already told you about it. Then phosphine, as I was saying you, that is phosphine.